Thank you for coming, even though there is a great workshop going on in 10 minutes. I'll be talking mostly about visual search, but also about Pokemons and our other fun stuff. And I hope my voice will join me for the rest of the talk as well. So my name is Ola. I'm a software engineer. I'm no data scientist, but I'm really big fan of machine learning and experimenting with that. And I work at Tipster. This is e-commerce company. We work on shoppable content. What it means is when you read the article, you can actually buy the products inside the article and not via affiliate links that direct you to Amazon or other websites with shops. We don't have the platform. I mean, we do have the platform, but our main focus is to sell products on publishers' pages. And there is a term, inspirational shopping, and I think it's really interesting idea, especially for us, because how programmers do shopping is that we do research for 2 weeks, we compare prices, we go to many shops, and then after 2 weeks or 3 weeks we buy something. Of course we don't buy t-shirts because we get them at conferences, but with other stuff we do it like this. And inspirational shopping means that you read the article, and it's an article, for example, about the trends for fall, winter 2019, and there is and the article says that brown hats will be the trend, and you think, maybe I need the brown hat, and there is a hat inside the article, and you can click on that, and there is a widget opening, and you can actually buy it inside. And if there is any performance issue or something is wrong with the page, the person closes the page and never comes back. So it's not like eBay or Amazon, because we go to eBay and Amazon when we need something and we realize that we need that. But inspirational shopping means that we need to take care of the performance. I also have the presentation about performance because of that. So let's start with an inspiration. Imagine that you go to visit your friend and there is a cool painting on the wall, and you take a picture of that because you think that maybe you need the same or similar painting in your apartment. And you post the picture into Pinterest or into Google, and there's a bunch of paintings similar to that one, and some of them are actually shoppable via Pinterest. So this is how visual search works. Usually when I ask people if they know what is visual search, they say no idea. But then if I ask again if they ever posted a picture, uploaded the picture to Google, for example, to look for something, most of the people know what's that. So I will talk about visual search in the content mostly of e-commerce today. And why now? Why we even need the visual search and not the textual one? Humans think with images. Our brain, the old part of the brain, processes the images faster than text. The study says that it's 60,000 faster. I'm not sure how they measure that, but it's impressive. And image is international, so you don't have to translate it. Image is the same for everyone. The meaning can be different, but if you see the picture of a dog, you don't need to think about if it's a dog or a dog in your language or Chinese or anything like that. It's international. So if you ever worked on textual search, you know that there are stop words in every language. So if you look for quote, for example, to be or not to be, it may happen that Elastic, that is the most popular text search engine, will return 0, because to, be, or, and not are the stop words of English language. So you can be disappointed with the result. And also, you need to translate the names and the descriptions. And if, for example, we are based on the Swedish market mostly, and sometimes in English the naming and the description is really poor. So the result from that is that it's very easy to find products on the Swedish market, but it's not so easy to find it elsewhere. So the whole translation need to be perfectly done to get it work, and you need to handle wrong images. And what I mean by wrong is, for example, imagine that you have shoes, and those shoes are white, black, and yellow, and you look for the white shoes. But the first variant, for example, has the black image, the image of the black shoes. And the result that you get is black shoes, even though you look for the white shoes. If you go inside the product, you will realize that there is a white shoe indeed, but the image is wrong. So with the visual search, you don't have this problem because you look by image. And this is our Vita score, famous example. Vita score means white shoes, exactly. And what Elastic does when we ask for white shoes, it takes the word white and takes the word shoes and looks for them separately and then merges the results. You can, of course, tweak the wages, you can a little bit tune up the algorithm, but this is what you get. And it's somehow related to white shoes, but I would say like half of the results should disappear from that list, because white is a color and shoes is a category, and Elastic doesn't know that because it's, for Elastic it's just text. So it looks for that in the name and in the description, and this is what you get. So imagine that you didn't take the picture of that painting and you come back home late at night, a little bit drunk, and you say, let's look for the painting, for the red painting. And this is what you get. Not so accurate, I must say, because it's really hard sometimes to even name what you look for, to even think about it. You don't always know what you're looking for, especially if we talk about abstract art, right? Or the clothes or something. Sometimes it's very hard to name and then to look for something. Is it even red? How many backenders here? Raise your hand if you do the backend mostly. And how many frontenders? Okay, so I will assume that it's backend mostly audience, and backend mostly audience usually loves that slide, because for like most of the people on the world, this color is red. But for merchants, those are the organizations who provide products, it may be burgundy or even memory of a sunset. There's no way that you could guess that. So for example, if you look for something and the name on the merchant page is memory of a sunset, even if you know that it's a color and you look for the red color, you won't find that product. We have the right hardware now, even though the computers were ready in 80s. And the machine learning is with us since 70 years. But right now, the visual search is blooming because it's cheaper and everyone can play with the tools that are available online. So there are no more excuses. You have plenty of tools that allow you to start free and then pay for what you use. I personally use the Google Cloud, but I know the Amazon's tools are great for starting with machine learning as well. And you have a couple of providers on the market. So no more excuses. Everyone can do it at home, and I encourage you to do that. But why now? Of course, it's driven by the money. But if you look at those logos, if you look at Amazon, for example, Zalando, this is Wayfair. This is the retailer of furniture and decoration. So this is e-commerce, and it's obvious that they sell stuff. But if you look, for example, at Snapchat or Pinterest, people don't go there to buy things, right? I don't go there to buy. But last year, they asked the users of Pinterest how many of them bought something via Pinterest. And it was 50% of the user. It's a huge market, just because they got inspired by the images they saw. And Google Lens, for example. This is not the place you would look for products to buy. I wouldn't, but it grows rapidly. So e-commerce is like the biggest player for the visual search. And inspiration and impatience, because we expect machines to read our minds. Like I said, sometimes it's very hard to know what we want, and we expect machines and machine learning to know that for us and show us the right products. During last conference, I met a guy who has a startup, and they suggest the right products to the customers. But firstly, you need to file a survey. And I said, no, it won't fly, because you need to do the work first. And people nowadays don't want to do that. I mean, if you look for electronics and, for example, for a very expensive computer, then yes, you would do that. But if you look for something, or even you don't look for something, and you want to buy, just, you have the good day and you want to buy something, then you won't answer many questions. You just want machines to read your mind and suggest something for you. So the impatience is a driver here. Couple of numbers, because you might think, all right, but we are developers. We don't care about money. We don't care about e-commerce. We don't care about selling stuff. Why we should even care? Because if it's driven by the money and this market will grow, then there will be more and more positions for software engineers to work on that. And because information received by the brain is 90% visual, and we process the images faster, way faster, because the old part of the brain processes images, and before we know how to read, we can process images, right? And 85% of viewers are more likely to purchase a product after watching a product video. 85%. Especially for fashion and for decoration, for example, the visual information is more important than text. So sometimes people don't even read the description. They just look at pictures. And this is my favorite. 62% of millennials want visual search over any other new technology. They want visual search the most of all. 62% of millennials. And these are the people who already have the money and who will drive the market. And 50% of responders preferred visual information, except electronics and spirits. I'm not sure about you, but I look at the statistic and I think it's about the IT people, electronics and spirits. But yeah, the rest of the world love images and they will purchase because of the videos and because of the images. So that's why we should care. So let's talk about tooling and let's talk about how we can work on image recognition and on visual search. Basically, there are two ways. One is image to text, and second is image to image. And the difference between those two is that in the middle, there are either the words that are understood by us, and the second is that in the middle there are just numbers that are understood by the computer. So image to text requires reading the features of the image that are the natural language words. And image to image doesn't care about human in the process. So the first way, which is image to text, is simply to prepare the tags or the features or the classes. This is the same thing. You prepare the huge training data. you train the model, and if your model is trained, then the uploaded image is processed by extracting the features from the features that you defined at the beginning, and you look for items with the same tags. So, for example, you have this nice dress, and this is the ready solution. I think it comes from Google, and Google says it's a clothing and it's dress and it's black. So if you process all your images this way, and then the user uploads the image, then it's translated into tags, into words, and we don't look through images, but rather we look through the products with the same tags. So that's why it's image to text. And I'm going to show you the simple image recognition. Very simple. I used for that purpose Python, because Python is like the default way, I think, if you start working with machine learning. I use libraries like Keras and NumPy to process the matrices and to use neural networks. I use Jupyter, and I usually do it on Google Cloud, but I'm going to show you the CoOp file. And I used a fashion MNIST dataset. How many of you know what MNIST is? Good. So for those of you who don't know, MNIST is a dataset of handwritten digits. And the problem with MNIST is that if something doesn't work on MNIST, it won't work at all. But if it works on MNIST, it won't always work on the real data. So MNIST is very simple. But fashion MNIST comes from, I actually have a slide for that. Fashion MNIST comes from Zalando. This is actually the data set of their real images of their products. And it has 60,000 of images in the training set. The test set has 10,000. All the images are in a grayscale 28 to 28 pixels images, and they belong to one of 10 classes. So here on this image, 3 rows represent one class. So here are the t-shirts, the jeans, for example. Here are the sandals. I'm not sure why they pick sandals, but hey, they can. These are boots, the bags, sneakers, etc. So let me now, with one hand, go to the CoOp, and I will just walk you through. It's like you don't need to understand everything here. I'm gonna put that presentation on Twitter, so you can follow the link and you can check that notebook on your own and run it on your local machine or in the Jupyter on your cloud. But then you need to import everything, then load the data. So here is you load the data from Fashion MNIST, and the Fashion MNIST comes from Keras. It's there, so you don't need to download it or send the direct link. It's there in Keras for you. So as you can see, there are 60,000 of images and 10,000 of images in the test, in the train set, and 10,000 in the test. And then we want to have the validation set as well. So we split, and we have now training and validation sets ready. Then you can just look how the products look like. This is not obligatory. Then you need to process the data a little bit. You need to normalize it. Here, for example, because all the images are black and white, so they have ones here as the last dimension. But if you process the RGB, then you would have 3 here, because you need 3 layers for each image. You normalize it so that all the values are between 0 and 1. You say that To categorical is simply processing the labels into vectors. So instead of having the label that it's sandal, you get the vector with 10 places, and you have 1 for the sandal and zeros in others. Then you build the model. This is very simple model. So you have like 4 layers here. I use the softmax. You can use the Sigmoid function as well. So softmax is it sums up to 1. So, for example, if you have 2 classes, for example, cats and dogs, and you upload the picture, and it says it's 70% for the dog and 30% for the cat. But if you use Sigmoid, then it would say, for example, 80%. It's a cat with 80%, and it might be a dog with accuracy of 70%. For example, so they don't sum up to 1. And then you train the model. As you can see here, we got more than 90% of accuracy with the validation set. Because for accuracy for the training model is 96, but it's a little bit overtrained every time you train it. But if we validate it, it's more than 90. So for simple images, it should give the accurate results. You will see that in a moment. And here is if you want to test it on your own, you just paste the link from the internet, convert it to black and white, resize it, and test what's there. So let's come back to the presentation. Yes, this you've already seen. So these are the examples. So as you can see, for simple images that are similar to the training data set, we get very accurate labels. So here it says trousers, and here it says sandal. Great, 100%. But it gets worse if you post the picture from the internet. It's not similar to the training data set. For example, here you have the dress, and the algorithm says is a sandal. Well, I'm sorry, it's not. And here you have the sandals that are on feet, and it says, well, it might be a bag, maybe a sandal, maybe a shirt, and maybe the boot. So it doesn't know what to do with that, actually. So if you want to use the simple training data like that, you need to test it. I mean, you need to be sure that it will be tested on the similar images. We will talk about challenges in a moment. You may also use the third-party tools. They give you diverse results and diverse pricing, but the API and SDKs provided by some of them are fairly similar. It depends what you need, because they give you different results. For example, like here, you have the same dress, and this comes from Google. This is Clarify, I think, and this is some other provider. And for the same picture, you get different tags. So I think only Google got the color right with 90%. Yeah, but the rest is missing the color. And for me, none of these are like, I'm not happy with any of this, because for fashion, probably the training set has all the images of the world, so it has also cats and dogs, and it's not into fashion. So I get lots of trash data, and it's not very accurate. So I was really disappointed with some of the tools. And if you already use the textual search, for example, if you use Elastic, you may go for image recognition for every image and enrich your data that you have in your database, and then just simply use the textual search for an end user. And this is cheaper, and also this is quite fast to implement. Okay, so the second one is image to image. It ignores the natural language, like I said. So you just use the model, or you can build it on your own, but it takes quite some time. You extract the features from the images, and then the same way, the user uploads the image, and the features are extracted from that image, and you look for the most similar features, which means that you look for the closest neighbors, for example. And I didn't implement that on my own. Because I found very good example on GitHub. This is called Simple Image Search Engine. It comes from Yosuke Matsui. He's an assistant professor at University of Tokyo. And how it works is it has two parts, offline and online. And the offline part simply processes all the images that are here in the image folder. It processes them, puts them into the feature folder, and then you run the server, this is online part, you upload the image of a dog or whatever, and then they are here, they are saved here, so you get them forever, and you can test it. Oh, and he uses the VGG16, which is the convolutional neural net, and it's trained on ImageNet. And ImageNet is a huge data set. So you remember the fashion news, it was 60K images, and here you have 15 millions, and you have 1,000 categories. So it's not very optimized, for example, for fashion, because it has 1,000 categories. It's collected by the people of the internet. People are amazing. It organizes the challenges almost every year, and it sets trends, because ImageNet is very important for the image recognition and the community. So this is how VGG16 looks like. It won a challenge in 2014, and you remember my simple model. It had like 4 layers, right? And here you have plenty of those. And it has also the 90% of accuracy. And you may say, hey, but you also got the 90% of accuracy. Yes, but it was 60K pictures and not how many millions? 15 millions. Yes, thank you. So this is very good model. So this is almost all the code. I love Python for that. So you need to resize all of them, you need to convert them into RGB, but the most important lines are here, where you define the model. You say that it's VGG16, which is imported here. The tooling is amazing here. You process the input, you subtract the values for each feature, and then you predict. So you build the feature vector for every image. And the example on his page on the GitHub was done on cats, of course, because cats are the royalty of the internet. And I did mine on Pokemons from Kaggle, because I always like to play with interesting data sets, because it's always more fun, like superheroes or something. So I will talk about challenges based on that on Pokemons. But if you want to use some third-party tools for image to image, it's a little bit more expensive. So brace yourself and go to your manager first to ask about the budget. But you can play with them. Not all of them are public, but if you go, for example, to Google Cloud, you can pay for what you use, and you can start for free. So it's awesome. So let's talk about challenges. The image quality, like you said, like I said and you saw on the fashionist example, if you use very simple images and very clear images, and then someone uploads an image like that, and you have no idea. If you know it's fashion, you may guess that it's about the jeans, or about the jacket, or about the shoes, for example. But if you don't know what is that, because it was trained on the whole bunch of images from the internet, it might be about the train rails, or the city, or curly hair, or whatever. So the model posture, for example, is a challenge here, because if you look at the fashion magazines, then people who are standing there, they don't stand like that. They are always like this, have this fancy pose. So then the model may look, if it's trained on the pictures like that, it may look for the models that are all in the fancy pose, instead of like looking for the clothes that are the same. So here you can see that the Pokemons are like, have similar posture like the Pikachu from the internet. The background noise. Here you even have like two objects. So you can see that, for example, this Pokemon looks exactly like the logo of the Pokemon Go, because there is like so much going on here in the background. So it's not clear that you are looking for this object. Training data versus real life. If you have very good quality pictures and someone snaps a picture of an idol during the concert, being a little bit shaky and drunk, and you need to look for the t-shirts, then it might look like that. Hangover Pikachu. So the results are not so accurate as well. Dataset relevancy. If you train your model on cats and dogs, and then you upload an image of a shoe or a hot dog, I'm not sure if you know, but there is an application, Is it a hot dog? And you can actually install that on your phone, and it says if it's a hot dog or not. And actually, it's biased by the ketchup. So if you have the ketchup, for example, on your shoe, the zigzag, the ketchup zigzag on your shoe, it will say that it's a hot dog, even though it's not. So here you have some random results from that. The color detection, as I said, in fashion, color is very important, but sometimes we are biased by the color. By the background color, for example. So the dominant color, it's not the object color. For example, here, if we cut the Pikachu first from the image, and then we look for similar Pokemons, it would be different, because now you can see that all the blue and pink from the background is also found, because Pokemons are pink and blue, and you have like, it's biased by the background color. If you have multiple items, also it may not look for the right object. So if I want to look for Pikachu here, but the model doesn't know, so you get lots of blue Pokemons, for example, because of that. And the color biased. Even though it's Pikachu, you get plenty of the blue Pokemons, because they are similar in terms of color only. And training data size is also a challenge, because you need diverse pictures from each category and subcategory. You need to group them by the department, and you need to take care of the response time. And for example, eBay has this problem, because if you look for like you look for an item in the whole data set, it will take forever. But if you know that it's, for example, a pair of jeans, then you will look only in the fashion department in the jeans type. So it will be way faster. So let's recap what we learned today. That visual search blooms now, and it will get more popular. Remember that millennials want visual search more than anything else in the internet. You can do it yourself. You can use the ready tools, or you can make a combo. You can play and tweak, and use still Elasticsearch, but like read all your images and extract features from them. And you need good quality images and large training set that will be similar to the images that will be uploaded by the users in the future. So they are not like perfect pictures, but then people start uploading stuff and it's something completely different, and you get irrelevant results. So I know you were curious, so I spent some time and I looked through all the 800 Pokemons, and I picked the ones that I think are similar to Pikachu. Machine doesn't support me in that, because I didn't see any results that were even close to that. But we may discuss that after the presentation if you disagree, for example. There's much more. So if you are interested in the topic of visual search or image recognition or Pokemons, then there is a bunch of links, and you can click on that. And remember that at the end of the day, it's all about math. So I presented the top-down solution here, but you can go bottom-up as well and learn about matrices, because machine learning is nothing more than a bunch of ifs and matrices put together. And you're awesome for staying with me this long and listening to this crazy stuff about Pokemons. Maybe you have some questions.
Thanks a lot. If we can maybe switch to the questions, I'm not sure there were any. Not at the moment. Okay. In the DataSphere. Okay, so if you have some, of course, you can send them there, but maybe you can just ask them live if there are any questions.
Do you have a plan on how to handle multiple clothes on a single image, like letting users select, or are you going to train the neural network to guess which one is important?
Yeah, these are two ways. The first one is asking user, like saying, hey, you have a pair of jeans, you have a jacket here, and you have shoes. What do you want? What do you need? And the second one is just to run the free searches in parallel. So give the results, but they can be like mixed, because it will create the like the trash result. But rather they should be grouped. Like if you look for jeans, here is a bunch of pair of jeans for you. If you look for shoes, here are shoes. So because if you want to look for everything, you won't find anything related.
I actually have a question. You used 4 layers, right, in your neural networks?
Yeah.
Did you actually experiment how much better you can get when you increase the number of layers?
Yes, and it because I had 4 layers, 2 layers with filters and 2 layers with max pool, which is like making the pictures easier to process. And if I added many layers, because I'm not data scientist and I'm not like I just played with that, so I experimented, and the time of training the model was way longer. It was like, because right now it's like 2 minutes or something, and then it was 15 minutes, but the results were similar. So I just came back to the 4 layers, because the 90% of accuracy is very good for this type of data set and this type of small model. If you know what you are doing, then you may also of course add the layers, but then the results might not be so accurate for you in the future.
Okay, thank you. Actually, those results would help in a startup where I worked 2 years ago, because we had text search and similar issues like you described. Any more questions from the audience? 1, 2, 3, no? Okay, well, let's thank again Ola for the presentation.
Thank you.
Thank you very much.